This is what happens when all stars die. The topic of the universe's ultimate fate is not about fear. It is not a prediction of doom for us, our children, or our civilization. The timescales are far too vast for that. Instead, it is an exercise in perspective, a way to understand the grand stage on which our brief moment plays out. By looking at the very end, we gain a deeper appreciation for the here and now. We see the light of our sun, the glow of our moon, the distant shimmer of the Milky Way, not permanent fixtures, but precious, fleeting treasures. This is a story of awe, of the profound, beautiful laws of physics that govern everything, from the first spark to the final silence. Imagine a clock unlike any other. Its second hand does not sweep every 60 seconds. Instead, each tick marks a billion years. With each slow movement, this cosmic clock brings profound change. The vibrant, star-filled cosmos we know will begin a slow, graceful fade. This process is not violent. It is a gradual unwinding, a slow cooling, a patient journey into darkness. The end is not a single event, but a series of long, overlapping epochs, each stranger and more silent than the last. We start this countdown not in terror, but quiet contemplation. The universe is a place of immense energy, constant creation and destruction. But thermodynamics, the rules of heat and energy, tell us this cannot last forever. Energy spreads out, becomes more disordered. That tendency drives the universe's final chapter. Every star you see in the night sky, every distant point of light in the cosmic ocean, is a massive celestial furnace. These are not serene, eternal diamonds fixed in the heavens. They are dynamic, violent, and profoundly creative engines of the cosmos. Each one is a sun, some smaller and cooler than our own, others hundreds of times more massive and thousands of times brighter. They are the crucibles where the very elements that make up our world and ourselves are forged. To understand the universe's ultimate fate, we must first understand the life and death of these stellar giants. At its core, it is a battlefield. A constant, titanic struggle between two fundamental forces. The first is gravity. A star is born from a colossal cloud of gas and dust, and its own immense mass provides the gravitational pull. Gravity relentlessly tries to crush the star inward, to collapse all of its matter into a single, infinitely dense point. It is a force of compression, squeezing the core to unimaginable pressures and temperatures, millions of degrees Celsius. But the star fights back with the power of nuclear fusion. In its heart, under this immense pressure and heat, the conditions become so extreme that the very fabric of matter is altered. The star begins to fuse the most abundant element in the universe, hydrogen, into the next element, helium. This atomic alchemy releases a tremendous amount of energy in accordance with Einstein's famous equation E mc2. A tiny fraction of mass is converted into a colossal burst of light and heat. That energy, in the form of radiation, pushes outward from the core, perfectly balancing gravity's inward pull. This delicate equilibrium, known as hydrostatic equilibrium, is what allows a star to remain stable. It is this balance that makes the star shine brightly for billions of years. Our own sun is in this stable middle-aged phase, known as the main sequence. It has been steadily burning hydrogen for about 4.6 billion years, and it has enough fuel to continue for another 5 billion. But this stability cannot last forever. A star is born with a finite amount of fuel. The hydrogen in its core is its lifeblood. Once this primary fuel source is used up, the delicate balance is broken. The outward push from fusion weakens, and gravity begins to win the long war. The star's long life enters its final dramatic stages. The exact path it takes from here depends entirely on its initial mass, the single most important factor in a star's destiny. Low-mass stars die differently than high-mass stars. For stars like our sun, The end begins when the hydrogen in the core is exhausted. Gravity compresses the core further, causing it to heat up even more. This new heat ignites the remaining hydrogen in a shell surrounding the core. The sudden surge of energy causes the star's outer layers to expand dramatically. The star will swell into a red giant, becoming hundreds of times its original size, engulfing the inner planets, including Mercury, Venus, and possibly Earth. Its surface will cool, giving it a reddish hue, but its total luminosity will be far greater. Eventually, the core becomes hot and dense enough to begin fusing helium into carbon and oxygen. This new phase provides a temporary reprieve, but the helium fuel burns much faster than hydrogen. After a few million years, it too is depleted. For a star the size of our Sun, there isn't enough mass to ignite carbon fusion. The star becomes unstable. In a series of final pulses, its outer layers drift away into space, creating a beautiful, glowing structure called a planetary nebula. Left behind at the center is the exposed inert core, a hot, dense sphere of carbon and oxygen called a white dwarf. This stellar remnant, about the size of Earth but with the mass of the Sun, is the first ghost of the degenerate era. It no longer generates new heat. It will simply spend trillions of years radiating its remaining warmth into the cold, empty darkness of space. Larger stars live fast and die young. When their fuel runs out, gravity wins the war in an instant. The core collapses, triggering a supernova so bright it can outshine an entire galaxy. The blast scatters heavy elements across space, providing raw materials for new stars and planets. What remains is either a neutron star or, for the most massive, a black hole. The stelliferous era, the age of stellar birth, life, and death, defines our cosmos today. But the gas for new stars runs out. Star formation slows. One by one, the existing stars burn out. The sky will grow dimmer. Blazing galaxies fade, leaving a graveyard of quiet, dark remains. The first great age ends. After the last star has flickered and died, the grand cosmic narrative doesn't end. It simply turns a page. The universe enters a new, unimaginably longer chapter, a quiet and contemplative epoch that will stretch for trillions upon trillions of years. The age of starlight, the stelliferous era, is over. Welcome to the degenerate era. It earns its name not from any moral failing, but from the bizarre state of matter that now dominates the cosmos. The universe is now populated almost exclusively by degenerate remnants, the compact corpses of stars. These are the white dwarfs, the neutron stars, and the black holes. Each is a testament to gravity's ultimate victory over the fires of fusion. In this era, the universe becomes a realm of profound, near-absolute darkness, a silent expanse punctuated only by the faint, residual heat of these dying embers. The age of fusion is a distant memory. Galaxies, once vibrant islands of light, become ghost towns of dead stars. Their once brilliant spiral arms are now just faint, skeletal traces, their gravitational structure slowly, almost imperceptibly, beginning to unwind over eons. Of all the remnants, white dwarfs are by far the most common. These are the spent cores of stars like our own Sun. At the beginning of this era, they are the brightest things left, glowing with a brilliant, white-hot intensity. But this light is a phantom. It's not born of new energy, as there is no fusion left within their cores. Instead, they shine with leftover thermal energy, the stored heat from a billion-year life of nuclear fire. Like cosmic embers plucked from a celestial bonfire, they now have but one fate: to cool. They will radiate away this stored heat over trillions upon trillions of years, a cooling process so slow it makes the entire previous age of the universe seem like a fleeting instant. As they cool, their light tells the story of their decline. Over countless millennia, their brilliant white light will soften to a gentle yellow. After trillions more years, they will glow a deep, somber red, like the last dying coal in a fireplace. Eventually, even that faint blush of light will surrender to the cold, and they will fade completely into blackness. Once it has radiated away the very last of its heat, a white dwarf is theorized to become something new, a black dwarf. This isn't a star anymore, but a cold, dark sphere of crystallized carbon and oxygen, frozen at a temperature just fractions of a degree above absolute zero. The timescale for this transformation is staggering, likely hundreds of trillions of years, perhaps even a quadrillion. It's a period so long that none could possibly exist yet. The universe, at a mere 13.8 billion years old, is far, far too young. When they finally do form, they will be one of the universe's most curious creations. Imagine a perfect, planet-sized diamond. These black dwarfs will be cosmic diamonds, the size of the Earth, yet containing the mass of a sun, all compressed into a crystal lattice. For these silent wanderers, drifting forever in the cold and dark, existence is almost entirely without event. But almost is not entirely. In the unfathomable emptiness, chance encounters can still occur. Over trillions of years, the orbits of two white dwarfs might decay, drawing them into a final deadly embrace. If their combined mass exceeds a critical limit, the dormant carbon and oxygen can explosively reignite. The result is a Type Ia supernova, a final, defiant flash of fusion. For a few brilliant weeks, a single point of light will blaze with the fury of a billion suns, briefly rekindling the memory of the stelliferous era before fading once more, leaving the universe even darker and emptier than before. These are the last gasps of starlight in a dying cosmos. As the degenerate era fades into deeper past, the universe changes again. Trillions upon trillions of years on, most remnants scatter or are swallowed by black holes. This marks the beginning of the black hole era. By now, the universe is incomprehensibly vast, cold, and empty. Black dwarfs and neutron stars sit so far apart they rarely interact. The only significant actors left are black holes, the ultimate victors in gravity's long war. Kings of a silent, empty kingdom. A black hole is a region where gravity is so strong that not even light can escape. They hold what were once clusters and galactic centers, adrift in a thin particle gas. But Stephen Hawking discovered black holes have a temperature, and they can leak. An incredibly slow fizz at the horizon means even these kings are mortal. Their long reign will end. In the profound silence of the black hole era, as these cosmic titans drift through the expanding void, another, far more subtle process may be unfolding in the background. It's a whisper of change, so slow and so fundamental that it challenges the very definition of matter itself. While black holes command the stage, this process works quietly, patiently, on every single atom left in the universe. It is a purely theoretical idea, born from our deepest attempts to unify the laws of physics. It's called proton decay. This concept isn't just a random guess, it emerges as a key prediction from what are known as grand unified theories, or GUTS. These theories propose that at extremely high energies, like those present in the universe's first moments, three of the four fundamental forces of nature, the strong, weak, and electromagnetic forces, merge into a single, unified force. A profound consequence of this unification is that the particles we consider fundamental and stable might not be. To understand the gravity of this idea, we must look at the heart of everything. Protons, those tiny, positively charged particles, sit in every atomic nucleus. They are the universe's primary building blocks. The number of protons in an atom's nucleus defines what element it is, from the single proton of hydrogen to the dozens and heavier elements. They are the architects of substance. They build the atoms in our bodies, the water in our oceans, the rock of our planet, and even the cold, crystalline structures of the dead stars adrift in the far future. The stability of the proton is the stability of the material world. In our everyday experience, and in every experiment ever conducted, we consider them eternal. No proton has ever been definitively seen to decay. Scientists have built colossal detectors, like the Super Kamiokande in Japan, which holds 50,000 tons of ultra-pure water, and watched, waiting for the telltale flash of light from a single proton's demise. Yet, after decades of observation, there has been nothing. These experiments have only proven that if protons do decay, their half-life is astonishingly long. Yet, if the grand unified theories are correct, this stability is an illusion of timescale. They suggest that over an immense, almost incomprehensible stretch of time, a proton can, and will, spontaneously decay into lighter, more stable particles. The proton would vanish, leaving behind particles like a neutral pion, which itself would instantly decay into high-energy photons, or perhaps a positron, the antimatter counterpart of an electron. This would happen on timescales of at least 10 to the power of 36 years. To put that number in perspective, that is a 1 followed by 36 zeros. Our universe today, from the Big Bang until now, is a mere 10 to the power of 10 years old. The predicted lifetime of a proton is a billion times longer than the current age of the cosmos. It is a timescale so vast that the entire history of stars becomes an insignificant flicker at the beginning of time. If this theory is real, then no structure made of atoms is permanent. All atomic matter is condemned to dissolve in the ultimate final erosion. The black dwarfs, those cold, crystallized remnants of stars like our sun, would not last forever. They would slowly evaporate, not through heat, but through this fundamental decay, radiating away atom by atom into a faint mist of photons and other elementary particles. Neutron stars, planets, asteroids, dust, every magnificent structure the universe has ever built, from the grandest dead star to the last grain of cosmic dust, would be subject to this inexorable erasure. One by one, over eons, their protons would decay, and they would simply cease to be. The universe, once filled with the complexity of matter, becomes an impossibly vast and thinning soup of the decay products. Photons, neutrinos, electrons, and positrons, all drifting ever further apart in the expanding darkness. The very concept of an object, of a place, dissolves. In this desolate future, only the black holes would persist, floating as the last bastions of structure in a universe filled with the faint, fading whispers of radiation from a long-dead material world. The final chapter of cosmic objects belongs to black holes. For eons they endure, but they are not immortal. Quantum mechanics meets gravity to give them a faint glow. This glow is called Hawking radiation. Pairs of virtual particles pop into existence. One falls in, the other escapes, carrying away a tiny amount of energy. The black hole evaporates, losing mass. A sun-mass black hole would take about 10 to the 67 years to vanish. The largest may last to 10 to the power of 100 years. As they evaporate, their temperature rises. Eventually, the black hole is warmer than the universe. Mass loss accelerates. In the end, a tiny flash of gamma rays and particles, and silence. With the last evaporation, the universe loses its final structures. The era is over. What remains after the last proton has decayed and the last black hole has evaporated? A universe at maximum entropy, the heat death. Not a death by fire, but by cold, stretched over unimaginable time. Energy so thinly spread that no useful work can be done, the unwinding of all complexity. A vast, cold, dark, near-empty vacuum with only a wandering soup of fundamental particles. Photons redshifted beyond sight, the sky, the day, the night, gone. Only a uniform, featureless, eternal blackness. A deeper darkness than before the first stars. No heat, no motion, thermodynamic equilibrium. No temperature differences, no engines can run. no chemistry persists. The universe settles into perfect perpetual rest. Why contemplate this distant, desolate future? It is not despair, but a tool for meaning in the present. Knowing light and warmth are finite gives them immense value. Every sunrise, every star, every moment of warmth is part of a temporary, brilliant phase. The heat death is a backdrop that makes today's complexity more precious. The same elegant laws that formed galaxies, stars, planets, and life also dictate their dissolution. Entropy, the move from order to disorder, is the cosmic author of beginning, middle, and end. This scale humbles yet liberates. We are a brief, brilliant moment when the universe knows itself. In that transience we find wonder, gratitude, and awe. We began with a clock, ticking in units of 1 billion years. We watched the age of stars and the long twilight of embers into the silent reign of black holes. We saw matter dissolve, and the last giants evaporate. The clock ticks into a future so deep that even a tick loses meaning. No change remains to measure, only a vast, cold expanse with a thin mist of dying light. The story is over. The great cosmic engine has run out of fuel. From a hot, dense beginning to a cold, empty end, the journey complete. There is peace in this final image. The actors have bowed, and the stage has gone dark. Why tell this story? Because on a small blue world, a species wondered what the lights were, and what they'd become. We are the universe's way of knowing itself. The ability to comprehend this vast story is a gift that connects us to all of time. It fills our fleeting moment in the light with deeper significance, and so the cosmos rests. No light, no heat, no motion. The true final chapter of existence.